today, as promised, we'll talk about the cone embedding problem and how it is related to some problems in quantum information theory. And we will start with yet another construction of 2-1 factors. It goes as follows. So assume we have a sequence of 2-1 factors. And we denote by tau n the unique trace on Mn. The unique ratio state. Each of these Mn's. And let us fix 3 alpha filters we did yesterday. And we do the following. So first we consider the phenomenon algebra, which is just L infinity direct sum of algebras Mn. So in other words, the elements of this sister algebra are just sequences of elements in Mn's which are uniformly bounded. And this is a good phenomenon algebra which sits inside. So if we assume that these Mn's are inside B of Hn, then this is a well-defined phenomenon algebra sitting inside the algebra of operators on the direct sum of these Hilbert spaces. So it has some good ratio states obtained by combination of these states tau n, but we will define a new one. So define that ratio state for omega on this phenomenon algebra by the following formula. So when we take an element here, which is just a sequence of elements in these 2-1 factors, then what we do, we apply this to each element xn. So we get some bounded sequence, and the main point of fixing this ultra filter is that then we can pass to the limit when n goes to this omega. And since this is a bounded sequence, this is a well-defined number. And one can easily check that this way one gets a ratio state on this phenomenon algebra, which is not normal. Well, then we define the outer product. So the outer product of these factors Mn is by definition the phenomenon algebra which we get out of these ratio states. Denoted by I of omega Mn. So by definition, we take the GNS representation corresponding to this ratio state, apply to this phenomenon algebra, which we and consider the bicompetent. So in fact, it turns out that one can make it more concrete because of this is already a nice phenomenon algebra. It turns out that you actually don't have to complete here, and you can more explicitly describe it as follows: that this is simply the quotient, the direct sum of this phenomenon algebra by an ideal consisting of all elements xn, such that if we take to n xn star of xn, then the limit will be 0 when n goes to this omega. So what can be shown is that that this is again a 2-1 factor. This is a 2-1 factor. But generally it's a huge 2-1 factor, so even if we start with something which sits in B of Hn for separable Hilbert spaces Hn, this 2-1 factor you cannot realize on a separable Hilbert space. And we're particularly interested in the situation when all these MNs are just our one hyperfine. Yeah?
Just a question to make sure. So when you write L infinity direct sum here, you just mean bounded sequences?
Yeah, I just mean bounded sequences.
Completion of the finite sums with the like spring bond or something like that, right? Bounded sequences.
It's bounded sequences, yeah. So to distinguish it from like C0, so like when sequences go to 0. Yeah. So by this I just mean bounded sequences of elements. Okay, so yeah, as I said, we'll be interested mostly in the case when each of these MNs is already a hyperfinite factor. So when Mn is equal to R for all n, so we write this R to the power omega for this product, outer product of MNs. Okay. So this is a convenient technical device to talk about like when you have to deal with approximate identities and you have to do some manipulations with them and pass to subsequences and things like this. So this turns out to be a very convenient tool to deal with such things. So what I mean is the following. So imagine that you have a sequence of elements, bounded sequences of elements in say R. Bounded sequences in R, and suppose say that their commutators go to 0 in the strong operator topology and goes to infinity. And then you want to do something with such things, but if you consider this as elements, corresponding elements in our outer product, well, first, these are already elements of L infinity, but we'll consider their image in the outer product. Then inside this outer product, you can simply write that xy is equal to 0. That's very convenient. And because this outer product is also 2-1 factor, you also have all the tools which you have for 2-1 factors to manipulate with these sequences. And you kind of don't lose much if you deal with outer products because that's useful remarks in general. That's coming from outer products, you can come back to the usual sequences because the general remark is as follows: if you have an element, let's call it Cn, and just in L infinity space, that's the usual L infinity space of n. And suppose this element Cn converges to some number C when n goes to omega. Right. Then, always by definition, you can still find a subsequence which converges to the same number, but only a subsequence. So then there exists a subsequence C and K such that C and K converges to C in the usual sense. So we can go back and forth between the elements like sequences in your original algebra to elements of the ultra products and then back to sequences in your algebra. Okay. So the cons embedding problem, or sometimes called, maybe more correctly, cons embedding conjecture, it says the following. So, as a conjecture, it says that every 2-1 factor m inside B of H with H separable embeds into R omega. We can find a phenomenon subalgebra of this huge 2-1 factor, which is isomorphic to our given 2-1 factor M. Okay. Yeah, at first this appeared as with many other famous conjectures, I guess. The first appeared as some sort of curiosity. So in one of the papers, Kohn just says that apparently this should be true. and not saying much more than that. But eventually it turned out to be related to various other important and delicate questions in operator algebras, and eventually also related to questions in quantum information theory. And so some of this, the goal is to explain some of this. It's not obvious from this formulation why should this be true at all. But remember that yesterday when we talked about injectivity, we said that like injectivity, it passes to limits. And so one could think that, okay, this is also some limit procedure coming from this injective factor, so maybe this is still injective, and then it would be certainly wrong. But it turns out it's not. I mean, this is not an injective two-word factor, and indeed it contains a lot of things which have nothing to do with amenability, injectivity. But we will see this eventually. So let me first to reformulate this problem. So it can be formulated in many different ways, and in particular it can be formulated without mentioning any outer products completely in terms of matrices. So let me call the proposition. Say that the following inside equivalent. So shows that Cohen's embedding conjecture is true. Right, but remember that the way we construct two-one factors, we just start with a separable sister algebra with a tracial state, and if we're lucky, then we get two-one factor out of it. Turns out that we can formulate it entirely in terms of traces on sister algebras. So another way to say this is that for every separable sister algebra, A and every tracial state tau, A, there exists just a star homomorphism phi from A into this R omega, such that this trace which we get on R omega, this unique trace, which I will continue to denote by this tau omega, gives us a given trace. So in other words, this tau omega composed with phi is given, it gives us tau. Okay? But in fact, then if we take this formulation, then we don't really have to consider all possible sister algebras, because like every sister algebra is spanned by unitary elements. So it's enough to take a countable collection of unitary elements which is dense in the unitary group of A and consider it as a kind of group representation. But then instead of some group, we can just consider group free group. So in other words, it's enough to deal just with one sister algebra. And moreover, then it can be formulated entirely in terms of just finite dimensional representation. So there's another way of formulating the conjecture is to say the following, that for every tracial state tau on the sister algebra of the free group with infinitely many generators, there exist finite dimensional unitary representations. Unitary representations phi n from this free group into unitary group of some finite dimensional space. So in other words, just a group of m by m matrices, unitary m by matrices, such that this core of G is the limit when n goes to infinity of the normal white trace of pi n of G for every element in the group. The claim is that every threshold state on F infinities can be approximated by simply traces on matrices. Which about this one? Yeah, yeah. Since we haven't discussed what we say after the formulation, what I mean by. So this is not the reduced, but the full, so-called full group system algebra of infinity. But let me comment on it in a few minutes. Finally, one could formulate it also in terms of just of the finite dimensional approximations. So okay, in this spirit, but now again for arbitrary system algebra. So one can say the following: that for every system algebra A, threshold state, so every threshold state or on A, and self-adjoint elements x1, xn in the unit ball of A1, every natural number m and epsilon larger than 0, we can find self-adjoint matrices x1 and so on, xn of certain size. We don't know also which are in the unit ball of n by n matrices. Such that the following is true, that if we take all these xi's and multiply them in some order, and apply our trace, then it will be well approximated by similar things for matrices xi1, xik, less than epsilon for all k not larger than m and all I1 ik in the index set from 1 to n. Okay. So in other words, in a suitable sense, the traces of products, of arbitrary products in our system algebra is well approximated by traces of products of self-adjoint matrices. So both formulation 3 and 4, they do not, they involve only finite matrices, do not involve any outer products. Basically almost all of it is just careful translation of the definitions, apart maybe from going from 1 to 2. So the technical issue here is the following, that in the formulation of Kohn-embedding problem, we started with a 2-1 factor. And here we claim something about arbitrary threshold state, which do not necessarily lead to factors. So they lead to non-factorial von Neumann algebras. So a general and not obvious result is that in fact, as soon as you have a von Neumann algebra with a faithful threshold state, you can actually embed it into a 2-1 factor in a trace-preserving way. And so that's basically how one goes from 1 to 2. And the rest is just careful translation of the definitions. Okay? So this, of course, does not explain why one should believe in any of these statements. So let us give some examples. And before giving examples, we need some definition.
Sergey, for other types, like there are other problems for other types of types.
I mean, one can formulate some analog, yeah, but if you want to use the hyperfinite to one factor, of course, you cannot embed other types here. But yeah, one can do ultra products of hyperfinite like 3 factors.
Even there are not known examples.
Known examples, counterexamples. Well, now we have counterexample to this in a way, so therefore.
No, but
Yeah.
if you embed it into an omega, then you get a trace.
No, but Lucas is asking if you take, say, type 3 factor,
Okay.
can you find one which is not easily like embeddable in something similar but in type 3 situation? Okay, yeah, let's give the following definition. Which is due to Radulescu. Let's say that a countable group is a hyperlinear. It's called hyperlinear. If it embeds into the unitary group of the ultra product from the algebra. Just so, in other words, there is this an injective homomorphism from gamma into the unitary group.
You raise the board.
Yes, I will raise the board and not write anything more. Okay, yeah. So if we look at this, why the name hyperlinear? So take a reminder. Recall that a group a group gamma is called linear if it embeds in a group of n by n matrices of some field. Some field K. So, and we'll see that this is, eventually we'll see that this is a weaker property, just defined in the name. So what then Radulescu proved is the following. So in general, if you have a homomorphism from gamma into the unitary group of the ultra product, it does not extend to the homomorphism of the von Neumann algebra of L gamma, but it turns out that you can always find another one for which it extends. And you find that if gamma is hyperlinear, then there is an embedding von Neumann algebra of gamma into the outer product in a trace preserving way. So such that if we have our trace to omega on this outer product and restrict to this von Neumann algebra, we exactly get this canonical trace which we discussed yesterday. It's regular representation. Like this. Right. So yeah, I'm not going to prove it not like we really need it, but maybe just give something about proofs, let me indicate the idea. So what we have to show here. So basically, as I said, what we need to do is the following: that if we have an injective homomorphism, we want to find another one which sort of respects the trace. So in other words, what it boils down to is showing the following. So we need to show that if say pi1 from gamma R omega is injective, then there exists another pi2 from gamma R omega such that well, we get exactly the canonical trace, which is specified by the condition that its value on every non-unit element is 0. That's what one has to show. So I'm not going to explain how to do it, but let me explain at the level of unitary matrices what you would do. So again, in terms of this kind of formulation, this means that we almost have a representation in the unitary group of n-dimensional space. And what we want to achieve is to find some other almost representation where traces become smaller, smaller and smaller. And so, in other words, let's do the following. So if you consider the unitary group of n by n matrices, I want to find another representation of this group such that for a given matrix, the trace becomes smaller. And the idea is the following. We have a homomorphism of unitary matrices of size n squared, which we think of unitary operators on Hilbert-Schmidt operators on Cn. Or in other words, it's Cn and so Cn bar. So that's why it's n squared. And the homomorphism is simply the action by conjugation. So if we take unitary, then we act on Hilbert-Schmidt operators by adjoint representation. So if you look at it, then you can easily check that if you compute the trace of the adjoint of U, it's actually trace of U squared, which is very nice. So as soon as your trace is less than 1, you see by doing this trick, you get yet another representation where trace becomes small. The only problem, this is not really injective. So if you happen to have some elements which are really just scalars, then this way you simply Q them, and this is not what you wanted to do. So an even better idea is to slightly modify it. So we'll take now really an injective homomorphism into U, but now of Hilbert-Schmidt operators of Cn plus Cn. And the homomorphism is U into the conjugation by the matrix U 0, 0, 1. This works even better. Now it's really injective. And the trace of this operator is now 1/2 plus 1/2 trace of U squared. So now it really for any non-scalar matrix, non-unit matrix, you'll get actually something strictly less than 1, and then take the square, so you get something even smaller. So using this idea, you can modify sort of your almost representation in unitary groups into some other things, getting closer and closer to the situation. Okay. Yeah, it's all fine, but do we actually have any interesting examples of hyperlinear groups? And in terms of what we do. Yeah?
So, do this one, solid and one. But I can't repeat this 2 chaotic
this formula and this
You can repeat it, yeah? You keep repeating it.
but then it's 1/2 plus something. So we have to go.
No, but this is a number which is less than 1, right? We're using this trick. You get it's closer to 0. I mean, as soon as you did it once, you actually can repeat just this one.
And then
Yeah, this you can do only like once, for example, just to get rid of, so that every non-trivial unitary operator has this quantity which is strictly less than 1. But then you can repeat this one, and every time it just keeps squaring.
and that happens to be injected. If I only
Yeah. I mean, if you already be not scalar, yeah,
okay.
of course. Or you can repeat this one; it's also fine. Oh, I mean, I see what you mean. That here, every time at 1/2. Okay, I said first time you do it, and then you repeat this. Okay. Yeah, let's have some examples where one can do and get such an impedance. Yeah, sorry. Before we go to the example, I forgot that. I promised to say something about the full group system algebra of a group. So recall, so we have the reduced one of a group, which is obtained by taking the left regular representation and taking the closure of closing this in the norm, completing with respect to the norm. But the full system algebra is obtained by taking all possible representations. So precisely to if you have a representation of gamma, unitary representation on some Hilbert space, then you can extend it to representation of the group algebra simply by linearity. And then you complete this group algebra with respect to all possible representations. So we find the norm of an element like this as a supremo over all possible representation phi of AG phi. And then you complete, and this gives you the full group system algebra of gamma. So in other words, it remembers all unitary representations of gamma. Okay, so yeah, returning to the question of constructing some examples. So we'll consider a particular class of groups. So let's say that a group gamma, and let's say a countable group gamma, is called residually finite. If there exists a sequence of homomorphisms of this gamma into some finite groups, gamma n, so with gamma n finite, such that the intersection of kernels of all these homomorphisms is trivial. And so the claim is that if your group is residually finite, then it's actually hyperlinear. This so every residually finite let's do it. So assume we have such a hyperfinite, residually finite group. So we have this homomorphisms such that the intersection of their kernels is trivial. So we can modify this a bit to assume that actually the kernels become smaller and smaller. So replacing gamma n by, say, the product of the first n and phi n by phi 1 by n. We may assume that the kernels become smaller and smaller. And such that the intersection is trivial. And once we do this, we can construct even many finite dimensional representations which have the right properties. So it will be even easier to find no homomorphism into the hyperfinite one factor. So namely, for each pi n, we can consider, so for each n, consider homomorphism of called sigma n from gamma into the unitary group of L2 over gamma n, which is simply the left regular representation composed with our homomorphism pi n. So when I G goes into the operator of the left regular representation of pi of Gn, sorry, pi n of Gn. So this gives us an embedding into just a unitary group of finite dimensional space, but this we can embed in many different ways into the unitary group of R. So for example, since we know that all hyperfinite to one factors, all injective to one factors are isomorphic, if you think of R as infinite tensor product, say of these spaces. Yeah. So we defined the hyperfinite factor using 2x2 matrices, but we did have to consider 2x2 matrices. We could start with matrices of any size. In any case, we are going to get an injective to one factor, and so it's always a hyperfinite to one factor. And so you can embed it, say, by simply identifying this with the first tensor factor here. So there are many ways of embedding this. So we now have this homomorphism, and notice that the point is that if we take trace of this operator, so this operator is the operator of translation on the space L2 of gamma n. So as soon as this element of the group is non-trivial, it actually does not fix any points. So in the corresponding matrix, there will be no elements on the diagonal. So the trace will be simply 0 if phi n of G is not the identity. Okay. So therefore, here we get our embedding. So our embedding of gamma, let's say gamma into the outer product simply sends sigma into this sequence, sends G into the sequence of these elements. And because of this property and the property that the intersection of kernels is trivial, we have that this omega, which is just the limit in this case of traces of these operators, is equal to 0. Is it okay? So, therefore, every residually finite group is hyperlinear. So we have an embedding So notice that for this result, we proved already more than what is claimed, so we don't need this previous result of Radulescu. We really embedded the group in the nice way, so it's sort of in a trace preserving way. So we don't have to even modify these embeddings. And it turns out that there are many groups with this property, and this property has nothing to do with amenability. So maybe a good exercise for a tutorial. I don't know, maybe it should be with a star, with a note, that proves that the free group with two generators is residually finite. What one really has to show, so the claim is the following, that if you take any non-trivial word in generators G1, G2, then you should be able to find some finite group with two elements such that the same word in these two elements is non-trivial, which seems to be possible to do. Right. Let's leave it aside. So as a consequence, we now see that the group von Neumann algebra of the free group actually embeds into this outer product. And as we know, it's non-immutable. But in fact, much more is true, and in a way justifies the name. So one can also realize the free group as a concrete group of matrices, even like two by two matrices, and then there is a general result due to Maltsev, which says that every finitely generated linear group is residually finite. So the consequence of all of this is that every countable linear group is hyperlinear. So we really have a huge class of groups which have nothing to do with amenability, whose group von Neumann algebras can be embedded into outer product factor. So Kohn himself observed that this is true for F2 actually, and on basis of this, because F2 is non-immutable, thought that it's sort of almost universal group, so this should imply that basically this is true for any group, and that was the basis of the conjecture. Okay, so and now we will connect it to a problem in quantum information theory, or one can say in foundations of classical quantum mechanics. So what we'll do is the following. Let's take two natural numbers and define the following quantities. So one, CQS and K, and QS stands for quantum spatial. And is defined as follows. So this will be a subset of 1. So we consider the following collection of numbers. Right. So it takes some time to write this. To explain what all this means. So where all these quantities are for. So we start with two Hilbert spaces, AHA and HB. Then this operates AX, for A from 1 to K. And this is a PVM projection valued measure on HA. So in other words, these are usually orthogonal projections which add up to 1. So the same with B, Y, B, so B from 1 to K. So this is a PVM on page P. And we have also, so in fact we have a collection of such PVMs. So all x, y are indices from 1 to n. And finally, x is a unit vector. Phi in page A times page B is a unit vector. So therefore, this is a subset of 0, 1 to power n squared k squared. So on the other hand, we can define similar things, but when we, instead of taking tensor products, we simply can require that PVMs are mutually commutative. We define another space called the CQCMK, and QC stands for quantum commutant. So the definition I said, it's basically the same, but instead of taking tensor product, we only require that they commute. So it's a collection of quantities AX, B, Y, Xi, psi, over all X, Y, A, B, where now H is a Hilbert space. Again, this AAX is a PVM on H. Similarly, BBY is a PVM on H. But all these XYs are indices from 1 to n. So psi is a unit vector. And I said that all this A and B's PVMs commute with each other. So in other words, AX, A with B, Y, B may equal to 0 for all X, Y, A, and B. So this is another set. Again, this is a subset of interval 0, 1 to power n squared k squared. So the question is which of these set should be thought as correlations for independent observations. So if you have a composite quantum system, then one can think that the underlying Hilbert space should be tensor product of Hilbert spaces, and then independent observables are simply observables living on one of the factors. But another possibility is that you don't try to decompose your Hilbert space, you just deal with one Hilbert space. And independent observables, independent just means that they commute. So the question is, which of these two features is the right one for modeling quantum mechanical systems? And it would be nice if they simply were basically the same. So what these sets then represent are kind of correlations between independent observations. So yeah, what one can show that both of these sets are convex. So the sets CQS and K and CQC and K are convex. It's easy to see, and it's also not difficult to see that this set CQC is closed. CQC is closed. it was also a problem for one time whether this is closed, and it turned out that this is not the case. So this is generally not closed, but still one can ask the following question, and this is a Sergey's problem. So is it true that at least up to this closure, these sets are the same?
Just a comment, like from the perspective of quantum computing, I guess we usually work in the set CQ, so there those Hilbert spaces are finite, but of course if you take the closure, then nothing changes.
Yeah, well, maybe additional comment that if we consider, so it's important that we consider infinite dimensional spaces, that if we require that all the spaces are finite dimensional, then these sets would actually be the same. So it's important to deal with infinite dimensional ones.
So when I say, when you restrict to finite dimension, I'm saying in the set CQS, we usually restrict to finite dimensional Hilbert spaces. Of course, when you take the closure of CQ, there's no difference between the closure of CQ and CQS.
Okay, yeah. Okay, so that was a problem, and it turns out this is actually equivalent to one's problem. So the theorem is the following. So first, so the following statements are equivalent. One's embedding problem conjecture. It's true. But then we'll formulate one more property, which serves as an intermediate step. So let me first write it, and then I will continue it later. So if we take this full group system algebra of F infinity and take the maximal tensor product with itself, then it actually coincides with the minimal tensor product or the spatial tensor product. So let me first finish the formulation, and then I will comment on this, and this is so-called Hillier problem. And finally, it's a series of problems, so in other words, or positive solutions to problems. So that the closures of these sets are really the same for all n and k. So a number of people contributed to this theorem, so there are more equivalent formulations, including Learn and Ivan. For here, so the first step, when it got kind of really interesting, it was due to Hillier, who showed that 1 and 2 are equivalent. It turns out that this question is equivalent to a number of other delicate questions about approximation local properties of sister algebras, which I will not try to say anything about. But yeah, before going to the main result, let me just say a few words about the Hillier problem. At least what does it mean? So yeah, so generally, if you have two sister algebras, then the easiest is to define their spatial or minimal tensor product. So what one takes is just the algebraic tensor product inside the algebra of operators on the tensor product Hillier spaces and completes and gets a called a minimal spatial tensor product. Turns out this is independent of how you realize A and B as a concrete sister algebras. Yeah. I mean, there are many formulations equivalent ones. So you can start with a rather large class of groups instead of F infinity. So there are some requirements. Yeah, but one way or another they should be related to the free group. But there are many options what exactly you can take. Okay, but on the other hand, you could do the following. You could start with just algebraic tensor product. And then start considering all possible representation of this algebraic tensor product on Hilbert spaces. And then complete this algebraic tensor product with respect to all possible representations. And what are representations of these things is, no way to say it, is that you have a representation of A on the same Hilbert space. And the only condition is that they commute. So that phi A commutes with pi B of B. So as soon as you have such pair of representations, then you get a representation, we call it pi A times pi B of the algebraic tensor product. And then this maximal tensor product is defined as a completion of the algebraic tensor product with respect to all possible representations. This maximal norm x, so if x is an algebraic B, is a supremum of norms of pi of A times pi B of x for all possible representation pi A and pi B satisfying this condition. And so for if at least one system algebra is finite dimensional, you don't see any difference. So if one of them is finite, the spatial and the maximal tensor product. So then you complete and then you get this maximal tensor product. So if at least one of them is finite dimensional, then they are the same. But as soon as you are infinite dimensional case, it had happened that they are different. Nevertheless, what is well understood is when you fix a system algebra and you ask a question when, for all possible V's, tensor products are the same. And this can also be, again, related to some inability, injectivity properties. But if you just fix two system algebras, it's kind of not at all obvious when these two things coincide. And so this question, Hillier proved a number of results which kind of indicated that this might be true. And he proved that this is actually equivalent to what's embedded problem. Okay, so recently there was a breakthrough result in quantum information theory, complexity theory, which proved certain things, which implies that Sirilson problem actually has negative solution. So this is the claim that MIT star is equal to RE. So certain complexity classes coincide. And this is a result of a number of authors. Gina, Drajan, Levidik, right, and Yun. And then it implies that the Sirilson problem has negative solution. So indeed, there are some n and k's for which these sets are different. And I will not try to explain this and even explain what it means, but the hope is that Ivan in his lectures will say something about both things and the implication. So in the remaining time, let me just say a few more things about the implications, and I also got the question, what is better? So I wanted to sketch an argument. The implications 1 implies 2 implies 3. Because in the end, this is what matters, right? Because if we now already know that this is not true, then we know that both this and these statements are not true from these implications. Yeah. Should I try to do this now, or defer to sort of tutorial? So yeah, maybe I will say some words about at least one implication, and then maybe the other one will do later. But before we do it, let me say that despite this solution, there are still several open problems around it. So although we know now that the Kohn-Embedding conjecture is not true, it's still a question whether other groups that are not hyperlinear. So this is one question. So there are no examples of such groups. And then there is another question in the formally smaller class of group, which is also not known whether there are anything beyond that class. These are so-called Sophic groups, which can be thought of as sort of generalization of residually finite groups. So maybe I'll say just a couple of words about Sophic groups. So there are certainly many groups which are not residually finite, and even about hyperlinear groups, one can find groups which are not residually finite. But there is another class, so-called Sophic ones, and they are defined as follows.
Sorry, can I ask a question related to this problem? So is this somehow the same as saying if conus is true for algebras coming from groups?
Yeah.
Is the same?
Yeah. So yeah, how it is defined? So we'll consider symmetric groups, and we'll consider groups which can be approximately embedded into symmetric groups. So formally, this can be defined as follows. So if we start with a symmetric group, we can define so-called Hanin metric on it. So the distance between two elements is the number of points which are normalized number of points which are not which act differently by themselves. And then, given a sequence of numbers, we can do a construction similar to our outer product from Neumann algebra. So we can define outer product of symmetric groups as follows. So we take just a product of symmetric groups, but then we divide out by all sequences Gn such that the distance from Gn to the identity goes to 0 when n goes to our fixed outer filter.
You mean 3 hours non-input?
Sorry? Yeah. So, sure. Okay, so the definition is kind of very similar to our definition outer products. So we have sort of product of algebras divided by sequences which goes to 0 in suitable sets. And these sequences which goes to 1 in suitable sets. And so a short way of defining the Sophic groups, which is a definition So the initial definition is due to Gromov, but the equivalent definition in terms of these outer products is due to Ehrlich and Schaber. And so forward, so a group is called, say, countable group. Gamma is called suffix. If we have an embedding from gamma into one of these ultra products for some mn and metodical. And one can formulate it again in just in terms of finite groups without any outer products. So let me maybe say it. So equivalently, this means that we have just maps. Let me call it sigma n from a group into the symmetric groups, not homomorphism, just maps, but which are almost homomorphisms. So in other words, such that the distance between Cn from GH and Cn GH CNH goes to 0 when n goes to infinity, and they have to be sort of away from 0. So this means that the distance from C and G and the identity should be larger than some number, maybe depending on G. So for n large enough, and all G not the identity. And in fact, similarly to Radulescu result, you can even assume that it goes to 1. So in this definition, it's not difficult to see that residually finite groups are actually sophic, and basically the same proof as we have for showing that residually finite groups are hyperlinear shows that every sophic group is a hyperlinear. So this again without due to Ehrlich and Schaber. But the proof is so like the main point of their work is that you have this equivalent characterization of Gromov result. Once you use this is almost immediate.
And this characterization in the limits does not, does the usual limit not come?
Yeah. It's just the usual limit here. You don't need omega anymore. And so another problem. So in principle, this class of sophic groups is smaller than hyperlinear, but again, the question remains: are there groups which are not sophic? These problems are still open. Okay, so we have like 13 minutes, so maybe I will try to explain. I mean, I won't be able to prove the result in any case, but I want to at least hand wave a little bit to make it maybe less mysterious. Okay. Yeah. So I want to sketch now the easy implication that 2 implies 3. And the observation here is for, so remember what we have to show. So we want to show that if we have that this maximal tensor product coincides with minimal one, then you have the same, or almost the same sets which you get from PVNs which simply commute, or which were obtained by taking tensor products. And maybe the first observation is that what is really PVM? So the PVM, just one fixed one, so a collection of k mutually orthogonal projections which adapt to 1. So such PVMs are nothing else as unitaries U on some Hilbert space with spectrum which consists consistent of numbers of rules of unity, so z in T such that z to power kk is equal to 1. And the correspondence is very explicit, so if you start with such a PVM, you can simply construct a unitary obtained by e to the power 2 pi I L over k. Sorry, not Pn, but A. Okay. So this gives us a one-to-one correspondence between unitaries with such spectrum and PVMs, or in terms of groups, this means that we have a one-to-one correspondence between PVMs and representations, unitary, or precisely unitary representations of the group Z of GC. Right, for just finite cyclic group. Okay? So if we accept this, now we have families of PVMs. This means that if we have n families of PVMs AX, A from 1 to k, then there is a one-to-one correspondence between such families and representations. So representations of just free product of these groups, or in other words, representations of the sister algebras. So representation of the sister algebra of this finite group, taken a free product of n copies of them. Okay. I mean, if you then accept this, then so what is the difference in the definition of this set? Right. So now we have a pair of two such representations corresponding to this PVMs A, and another pair corresponding to the PVMs B. And on one side of Tirizian conjecture, we consider just tensor product. Right? On the other side, we consider other representations which computes. So in other words, on one side, we consider representation of minimal or special tensor product of such algebra with itself. On the other side, we consider just maximal tensor product. So therefore, we would be done if we had the analog of this Hilbert conjecture, but now for this group instead of the free group. Right? So therefore, we would be done. Now, if so, let me call this group just if I don't repeat all the time this notation that sister algebra of this group, maximal tensor product with itself, coincide with the minimal tensor product.
You need a bit more, right? The correlations only tell you first order, the states on the.
Well, I think I'm not saying it's equivalent. I think that would be enough to have that smallest set, right? I mean, so if I wanted equivalence, that would be not quite true, but I think for equality, that would be enough. And we have we have the same thing, but for free product instead of free groups. So it just remains to see that we can pass from free groups to, from free groups to these groups, and yeah, here one has to do something. So this is not automatic. So let me say what's a possible way how to do it. So the point is that we can, if we start again just with one group, ZKC. So of course, if we take the sister algebra of Z, then this will be a quotient of the sister algebra, right? Because it corresponds only to representations where the unitaries have spectrum consisting of roots of unity. But this homomorphism is easier to split using the UCP maps. So we can find a splitting phi, which is UCP. So a section of this map. And this is kind of easy to do by hand, because if at the level of, if we pass to Fourier transform, this just means that okay, you have functions on the circle, which is this one. And here you have functions on roots of unity of order k. Yeah. And you have the restriction map. This is our homomorphism. Right? So this is the restriction map. And I want to find a section of it where I can do it in a very explicit way, like if I have a circle, or if I have this roots of unity, I can cover the whole circle by small open sets. Consider corresponding partition of unity, and simply if I take a function here, map it into a function obtained by this force. So f of e to the power 2 pi r a divided k rho k, rho a. So this gives us an explicit UCP map, which is left inverse, right inverse to this map. Yeah. Okay, this you can do just for one, but now, and here, as I said, I'm not going to really prove the result. So a general but a non-trivial fact that you can take three products of UCP maps, and they will still remain UCP maps. So by taking three products of UCP maps, we can factor the identity map on group sister algebra of this gamma and k as the following. So we start with this one. So I said, then we take free product of this map. So we'll go into sister algebra of the free group with and generators. This we can simply embed in the sister algebra of the free group with infinitely many generators. Right, and then go back to our sister algebra. And because you can do it through this infinity, and you know the result for this one, you get the result for this sister algebra as well. Hence the result. Okay. So this proves that Kirchberg's problem implies Tillotson problem, but we still have to want to see why Kohn-embedding problem actually implies Kirchberg problem. I think we'll discuss it at the tutorial.
Any questions?
I got a little bit lost at the end there. Can you remind me which of the two Janitor products corresponds to the quantum spatial and which corresponds to the quantum computing model?
Spatial is just when you take tensor product of representations. And commuting just means that you have representations on the same space, but we have commuting images. So spatial always means that you take like tensor products of spaces.
So quantum computing is the maximum.
Yeah, it's the maximum.
Now let's thank the speaker again.